Okay, I guess the natural first question is who am I and what am I doing here? So I'm Bill Bird, and I teach a lot of things around here, but I actually haven't gotten a chance to teach Senge 265 in about 4 years. And it makes me sort of jealous sometimes because 265 is such an interesting course. And so, whenever somebody offers me the chance to do a guest lecture, I sort of jump at that. So I was asked in August, hey, Bill, can you do a guest lecture in 265? And I thought, well, that's obviously a good idea. But of course, in the age of COVID and whatever, it used to be when you gave a guest lecture, you got to bound into the room and bellow at people for an hour, and that's a lot of fun. But these days, a guest lecture apparently means me recording a video, because it turns out, due to some scheduling issue, it wasn't really possible for me to show up and do the lecture live. So I'm sorry about that, but if it's any consolation, we could get to talk about regular expressions, which is one of my favorite parts of 265. Don't get me wrong, I love talking about C, I love talking about Python and Git and things, but regular expressions are lots of fun, and I always found it a little bit weird that they were sort of stuck in 265. But it makes a lot of sense if you think about it, because regular expressions are a way to save time. They're a way to save time both in the time it takes to develop a solution, but also in the time it takes to maintain it. And so I want to start by proving that point. So fundamentally, what we're going to end up talking about is pattern matching. So let's talk about working with data. And often, especially up to this point, if you've taken first-year courses and things, you've worked with data. You obviously covered file input and output in first-year programming. You probably, I imagine your current assignment sounds like it's pretty data-intensive. But often the way you work with data is you go from a very organized, machine-readable representation to a human-readable one. And so a common one might, frankly, a first-year programming exercise might be, here's a data file. You can expect that the first line contains column headings, and every subsequent line contains, each row contains 3 entries, 2 numbers, and a string. Okay, and that contains, I guess, some weather data, so a latitude-longitude pair and the conditions at that location. Okay, great. So you read that, and then you print some kind of formatted output representation, something human-readable. Very common first-year programming exercise. Go from a easy-to-read format for a machine to something more convenient for humans to read. Okay, so that maybe at this level is an easy problem. Now, another easy problem, I guess, is to generate a human-readable representation in the form of HTML, which is not very readable, obviously, by itself, but can easily be rendered by a browser. Okay, so the idea here is that because it's so easy to pull that input in from the input file, it is really easy to generate it in whatever output format you want, because all it comes down to is writing output formatting statements. Okay, but that's not what I want to talk about. What I want to talk about is times when you sort of have to go in reverse. So suppose we wanted to start with that first example and work backwards. I give you a formatted, human-readable representation, and your job is to write a program that goes backwards from that to a sort of spreadsheet-style machine-readable representation. Well, that's not so tough, as long as you have a lot of ironclad assurances about exactly how that input will look. So often when you work with these human-readable things, you have to take into account human error. So if a human is actually producing this, then there's the potential problem that they don't do it correctly, that they miss, you can't expect there to be a hyphen there or something. But if you can expect that, it isn't that tough to write a program that parses this. It's tedious, certainly, but it's not that tough. What about this? What if I hand you an HTML page and I say, I want to extract all the interesting data from this? So there's a piece of data I want, there's a piece of data, there's a piece of data, this. In other words, discard all the junk, discard all of that HTML garbage that's only there for formatting, and pull out the meaningful information, the salient part of the data set. Okay, I don't know if that's necessarily any harder than this, but it's certainly really annoying to solve. And in the best of times, this would be an extremely tedious problem. And you can't necessarily resort to some of the tricks you'd be able to in a lot of other contexts. For example, I've tried this myself. It isn't always really that feasible to try parsing HTML like an XML file or something. Python has built-in XML functionality. You could try that. The problem is it's often too strict. The majority of HTML written in the world is not written properly. And so what you want to do is have some reasonably flexible way of going through this input data set and yanking out the important pieces of information. What you really want to do, I think, is pattern matching. you don't really care about most of this junk. You don't care about this at all. You don't necessarily even care about things like this. What you care about is being able to identify where are the lines that you want in your output file. So every time maybe we see this tag, we might notice that seems to be the beginning of a new line. I guess you could also use this one over here for that. And then where are the individual cells of my spreadsheet? And it turns out the TD tag is the tag for an individual table cell in HTML. Maybe we could just use those. Maybe instead of trying to parse this from start to finish, we could basically do a find operation, go searching for every area that matches a specific pattern. For example, if I want one cell of my table, I would look for a TD tag and its closing tag. And then I would go and pull out whatever's in the middle. Okay, this is now a pattern matching task. And the reason this is important is that we do a lot of pattern matching. You did pattern matching in first year programming, and it turns out it becomes really important later on for a lot of very strange reasons. It shows up in lots of different courses in different ways. Not only does it show up in an applied sense because you often have to scrape data off of the internet, so there might be data displayed on a web page somewhere, and you actually want it in a machine-readable format. That's a pretty practical reason to need it. But also because it turns out the way that we do pattern matching, and spoiler, this is what regular expressions are about, shows up in strange places like the Foundations of Computer Science course, so deep theory. And that's because it turns out there's actually a fundamental aspect of a regular expression that we can tie together with some of the theory of computer science. Okay, so what's pattern matching? Well, let's think about this. Let's think about writing a Python function, we'll just call it match. Let's write a Python function that takes a single string and decides, so it doesn't need to do anything else besides answer yes or no, it decides whether the string obeys these various properties, just one at a time. So we'll write one function to decide, does the string begin with AA or EE? So we'll just worry about lowercase. Okay, second idea, let's decide whether the string contains one or more words where each word contains only letters. So the words are separated by spaces. The next one is all occurrences of the letter A in the string come before any occurrence of the letter B. Now, what this actually means is a string like A, B, C, D would work because there are no A's after the first time you see a B, but the string B, 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 B would also work. Because as long as there's no A after the first time you've seen a B, the string passes the test. And I know these are contrived examples. What I want to illustrate is that we can easily solve all of these, but that it requires a surprising amount of energy to solve these different problems, even though they're all basically just pattern matching. Then what about, are we looking at a single HTML tag? And that includes not only standard looking tags like this one, but also weird situations where you've got properties of the tag like a style. Strings that contain each of the vowels in the English language, that's A, E, I, O, and U, exactly once, and they appear in order. So the first vowel in the word is A, then E, then I, then O, then U. And then finally, and this is a nightmare in general, we'll do a brief example of this later, decide if the string is a C variable declaration. So, I mean, here's a nice friendly looking C variable declaration. I don't know, here's another one. That's nice. But then there's this horrifying mess, which is actually a valid C variable declaration, although we won't worry about how to pattern match that. It's possible. If you ever write a compiler, you'll have to worry about that. So, does the string start with two E's or two A's? Here's a function I might use for that. Starts with E or AA. Well, there's this method that's defined on string objects that tells you yes or no, does the string start with particular characters? So I'll just use that. Does the string start with EE or does the string start with AA? Done. Pattern matched. Okay. And here's some examples just to prove my point. Okay, great. So we can solve this problem. And I mean, again, these are on the easier side for like, 110, well, not this one, 110 exam questions for the most part. Okay, so there's that. What about, does it contain only words? We can still do that. We can solve this problem. So the way I would do it is, knowing what I know about Python strings, I would split my string. The default split method just splits by all possible whitespace characters. And then I would take a look at each of the pieces that it comes up with. So if my string is hello world, then the pieces that split would come up with were the string hello and the string world. What I want to do is then iterate over that array it gives me, that list, sorry, I've been teaching C for 4 months, that list that it gives me, and just decide is each of these tokens that it produces consist only of letters. And so I'll loop over the tokens and I'll just ask the question dot is alpha, which is defined on the whole string and just returns true if everything in the string is some kind of letter, uppercase or lowercase. Okay, great, pattern match, we solved that one too. The thing is, maybe worth noticing, is that deciding if the pattern is matched isn't the same problem as doing something with the pattern. So I guess I could go from deciding if the string is a bunch of words to extracting each of those words. But I don't know if it's that easy to, for example, substitute something for each word using the same methodology I've used here. Because this is a bit destructive. It splits the string up into words, but it doesn't maintain any information about what was between each word, how many spaces, for example. But for now, let's think more about matching. So we can definitely match this pattern. Okay, what about all A's appear before all B's? Okay, here's an example of that. So what I'm going to do is just use a flag. I have this variable found B, and I'll just walk along and I'll keep track of when I've seen a B. And then after that point, if I see an A, then we're in trouble, right? Then we've got a problem. Okay, so I'll do that. And I just loop over the string. If I see the letter B, then I'll set my flag. And then if I've seen the letter A, and I notice that there was already a B before that, then we've got a problem. Then I return false. And so, okay, I can match this pattern too. It's not that tough. The problem is, notice that for each of these problems we've done so far, I've had to solve everything from the ground up. Even though they're all pattern matching, I basically had to come up with a brand new solution every single time. I had to repeat the entire process of engineering my solution every single time. Not only that, much worse than that, frankly, what happens if I make some relatively small change to the requirements of my pattern? For example, all of the A's and B's occur before any C's, or all of the A's occur before the B's or the C's. It could be that that requires me to completely overturn everything I've come up with so far. Slightly different patterns might have completely different match functions. So pattern matching is possible. We can do it. We can write code that matches patterns. The problem is having to do it from scratch every time is tedious, and it can sort of cause a maintainability hazard. Because if somebody comes back and has to look at all of our pattern matching code, they now have to retrain themselves for each different pattern. And the code that you write for each different pattern not only will be different between patterns, but different between people. Because it's just general code if we write it in this style. And we know that individual programmers have different styles of writing code. So here's my solution to the vowels in order problem, and I think this might give an example of why these characteristic solutions can be dangerous. So the way I've decided to solve this is I want to ask, does the string of text contain every single vowel, A, E, I, O, U, exactly once in order? So because I only care about the vowels, the way I'll handle this is I'm going to make a secondary string where I just pull in only the vowels from the string I'm looking at. And when I'm done, I have the string of all the vowels in the original string, and I just want to ask, does this string equal A, E, I, O, U? If it doesn't, then the string doesn't match. So A obviously is not. If I look at this word here, A, E, I, O, U, so if I pull the vowels in order, I get A, E, I, O, U, and so this string would match. So that's one way of doing it, but maybe I hopefully have proven my point by now that yes, we can match these patterns. The problem is if we have to start from scratch every time, that's not very sustainable. It's tedious, it's fatiguing, and there might be a bit of a maintainability problem because somebody that comes back and looks at this code, even if it's you looking at your own code, may not quite understand what you did because each pattern is matched in some ad hoc way. The techniques you use don't really have anything in common. So what do we do about that? So it turns out there is this thing called a regular expression, which is a uniform, and really this is the only thing I care about for the time being, uniform way of describing a pattern that can then be matched. It's true that it's also compact, maybe a bit too compact. Regular expressions are known to be rather cryptic when you're done. They're sort of a write-only language. And they are efficient because you write the pattern and you leave it to some library to figure out how to deal with that pattern. And as usual with libraries, if you can trust the library is doing things correctly, that means you, the average everyday programmer, don't necessarily have to worry about these thorny issues of things like complexity. So I'd say it's all three of these things, but uniform is a big deal. It means whenever we want to match a pattern, we have one syntax to use. And there's to some extent, I'm lying about that because there are variations in regular expression dialect, but if you're writing your regular expressions in Python, and so is somebody else, you and that other person will be using a common syntax, and I'm mostly going to discuss the regular expression syntax used by Python. So the other advantage of regular expressions is that you write one expression that you can use to match a pattern. But you could use that same regular expression, that same description of the pattern to perform tasks like extracting data, like that earlier example with the HTML, or doing search and replace. So you don't have to rewrite everything just because the reason you need the pattern has changed. But before I talk about Python, I want to talk about this ancient Unix utility called grep. You may well have already seen this in 265. Certainly if you haven't already, now's a good time to do it, because grep is really useful for command line stuff if you ever need to search something. So as an example, you'll have to use your imagination for what this file contains, but suppose I have a file called englishwords.txt, and it just contains a list of English words, one per line. What grep does is it, either from standard input or from a file, it reads the lines of input and it asks a question, does each line match a pattern that you provide? And any lines that do match get printed out. Usually if you do this yourself in the terminal, it'll even give you some nice colorful representation of what part of the line matched. So any line that contains the pattern that you ask for will get printed out. So in this case, the pattern I'm giving is just a bunch of regular characters, and so it just prints, it turns out this is actually a regular expression, but it's a pretty basic one. It's just asking, does the line contain YTHO? And this is the list of lines that get printed out. All right, so I want to start with this as the most basic forum for talking about regular expressions, because hopefully the idea of searching our list of English words is easy to identify with. So this is, YTHO is a regular expression. The most basic fact about regular expressions is that when you put a literal character into one, like the letter Y will match the letter Y. So if I go searching for, if I just want to search for a piece of raw text, that is by itself a regular expression. The reason regular expressions are more powerful is that we have extra symbols we can add to denote more complicated cases. We call these things meta symbols. In this example here, I've used two different meta symbols. This meta symbol here, I think I'm going to get ahead of my slides a bit. Maybe I'll fast forward. So this meta symbol here, the caret, which is shift and then the number 6 on your keyboard, will match the beginning of a line. So we know that in a file, the beginning of a line is sort of an invisible, there's not really a character that goes with that. But if we view the beginning of a line as some sort of invisible thing we can match, the caret will match that. So if I'm searching for the pattern beginning of line XY, the only lines of the file that will be matched are lines beginning with the characters X and Y, not just with the characters X and Y in them somewhere else. And that turns out to be the words xylophone and xylophones using this dictionary. Similarly, there is this meta symbol, the $, which matches the notional symbol at the end of a line. And so if I search for BA $, I'm searching for lines that end in the characters BA. And so these are pretty simple examples of meta symbols that I can use in regular expressions. And that's true in grep, and it's also true in Python. Now, I guess that begs the question, but wait a minute, what if I actually want to look for this character in a line? What if I'm searching a line of text and I actually am looking for this or looking for a $? So the usual rule, just like elsewhere, is if you want to search for the literal character, you have to escape it. So you use \caret or $. And we'll notice going forward that regular expressions end up getting quite bogged down in backslashes as time goes by, because there are lots of characters that we use as meta symbols, but there are also times we want to search for those characters literally. Another meta symbol is the dot. So the period character is a meta symbol that matches literally any character. So if I search for the pattern A.B.C, what I'm searching for is any sequence A followed by something. I shouldn't put a question mark, that's a different kind of meta symbol. A and then something, and then B and then something, and then C. And so we can see it matches things like the middle of drawback or the middle of barbecue. So the dot is actually a very powerful meta symbol. We don't often use it by itself. We often use it in combination with something else that we'll see in a couple of slides. And so here's another example of that. If I search for A.Z, what I'm searching for is any 5-character sequence where the middle 3 characters are irrelevant to me, but the first one's an A and the last one is a Z. Here's some more examples. Let's search for complete lines that consist of a word beginning in Q followed by 3 other characters. So it's a complete line because I'm putting beginning of line at the beginning of my pattern and end of line at the end. So it will not match lines that just begin with a Q. It'll only match lines that begin with a Q and end 3 characters afterwards. And so I get these, and then let's search for 4-letter words that end in Z symmetrically. All right, so now let's talk about quantifiers. So we've seen it, there's examples of some meta symbols that match characters, like the dot matches any character. There's the caret and the dollar sign that match these notional beginning of line and end of line symbols. But there's also there are a variety of different ways of quantifying the meta symbols that you're using, or other things. And one of them is this character, the star. Now the formal term for this is clean star, named after somebody named Stephen Clean, who didn't pronounce his name clean, he pronounced it Claney. Not Clean of Kleenex fame. I don't have nearly enough time to explain what really is going on there, but we call this thing a clean star. If you want to learn more about the clean star, try taking CSC 320. So the clean star takes the thing before it. So here's the star here. I'm attaching the star to this S. What I'm telling the expression is I'm saying I would like to match the character S 0 or more times. So if I just write the letter S by itself, obviously what I'm going to match is the letter S. If I write the letter S followed by a star, I'm saying I want to match 0 S characters, 1 S, 2 S's, 5 S's, 1 million S's. I'm allowed to take as many of these as I want. And we can see it matches prince, princess, princess, and then part of the word princesses, but not the whole thing, because there is no ES at the end of my pattern. And so the clean star matches 0 or more times, and I can't tell you how often people get that part wrong. So when people use the clean star, it's really, really easy to make that mistake and assume, oh yeah, if I want 1 or more S characters, I'll use a star. But the clean star is able to match 0 S characters. So it's 0 or more, not 1 or more. In Python, not in the normal grep, but in Python, if you only wanted matches with at least 1 S, you could use this meta symbol, the plus. The plus is a 1 or more variant of the clean star. If you also, in the grep syntax, if you want to match at least 1 S, you don't want to allow the 0 case, you can always double it up. So match PRINCES, and then 0 or more other S characters. So you could always do that. So there's no reason why the 0 or more thing necessarily ruins anything for you. You just have to make sure you keep that in mind when you're writing a pattern. There's also this meta symbol, the square brackets. So if I put a set of things in square brackets, what I'm saying is match one of the things inside these brackets. So to be clear, the thing I'm circling here, this isn't going to match one character, and the character it matches will be any of these 5 things, any vowel. And you'll also notice in the middle here, I'm using dot star. So the way I would read this pattern is match beginning of line, then a vowel, so 2 vowels. So here's AU, for example. Then match any sequence of other things, and then 2 more vowels. And so here I notice that I've got AU, and then a D, and then IO. So the dot star would match this D. I've also got eigenvalue, EI, those are both vowels, and then UE, those are both vowels. The dot star eats up everything in between. And the typical rule with regular expressions is when you have a quantifier, the quantifier can stretch or shrink as needed to make sure that the pattern ultimately matches. So as we've seen, there are lots of other vowels inside of this word. But because the pattern is asking for begins with 2 vowels, ends with 2 vowels, those sort of get set in place, and the dot star eats up everything in between. And then end of line. So that's the square bracket meta symbol. And inside of square brackets, if you don't want to have to write A, B, C, D, E, F, G all the way up to Z, you're also allowed to specify ranges, as long as the ranges are natural, so within the alphabet or digits or something. So A to Z, and then lowercase a to lowercase z, if you don't want to write each thing out individually. Inside of the square brackets, if the first character in the square brackets is the caret symbol, you are inverting the character set. So what you're saying is, instead of match, an example here, if I put this in square brackets, I'm saying match any of these characters. If instead I write this, I'm saying match any character except for one of these. And so what the pattern on the slide is currently doing is it's saying match the beginning of the line, followed by any character other than a U as many times as you want. So as many characters as you want that aren't the letter U, and then OU. Okay, so we get things like thou and bayou for that. And then another example, if I look at a pattern like capital A, capital Z, and then not capital A through capital Z star, what I'm basically saying is I want something that begins in a capital letter and then has no other capital letters afterwards. And so this string would match, this string would match, but this one wouldn't because there is a capital letter afterwards, after the initial one. And so, not that we care too much, I guess, but the name grep, the reason we have such a bizarre name for a pretty standard program that we use all the time to search stuff, is that it comes from this ancient Unix editor called ed, from which I believe in 265 people still teach vim. So vim, which is descended from vi, which was descended from ed, has actually inherited this command. It turns out in the old Unix editor ed, if you wanted to use a regular expression to search for something, you would run this command, g, then a slash, then the regular expression you care about, and then slash p. That would print out all instances of that regular expression in your file. And it turns out you can still do that. If in vim, you could run that command if you wanted to, because vim has inherited that set of commands. Over time, people were noticing they kept opening their editor just to do searches, and so they wrote a script which became a program that basically backdoored into that and then would run that itself. And they called the program grep as an abbreviation for the command that they were using. And so this is pointing that out. So here is an example of a regular expression to match that problem from earlier of seeing all English vowels in order. And maybe it's clear that this is a lot. And I'll go through some examples in a few minutes that describe how to design these things. And hopefully, once we've seen how to design them, it'll be clear that, yeah, it's not fun to read a regular expression, but as long as you develop it iteratively, it actually can be quite easy to write them. Okay, so what about Python? So in Python, there is a module called RE that implements regular expression functionality, and it's great. The Python regular expression library is fantastic. The syntax used for Python regular expressions is a little bit different than that used for grep. Although all of the stuff I talked about for grep today, it's pretty basic stuff in the regular expression world, that would work in either grep or Python. The more advanced things I'm going to talk about, the Python ones, they would not necessarily work in grep. So just be aware of that. It's not as big of a deal these days, but there are actually quite a few competing regular expression syntax implementations out there that do tend to diverge quite a bit with more advanced features. So I'll start with this function re.match. re.match takes a pattern and it takes some string to work on. And it returns either this specialized match object if the pattern does match, or it returns none, which, as you might know, is the Python analog for a placeholder value that represents no data, like you might use null in a language like Java or C. So you could use the fact that it either returns an object or none as an easy sort of yes-no test for whether a match exists. And I realize as I look at this slide, I owe you an apology. So you'll notice these are slides that I haven't used in a couple of years. I've adapted them, but one of the things I remember is that the slides are full of these sort of weird Halloween-themed references. I think it's because last time I gave a lecture on this, it was like late October, so sorry about that. Not very timely references. I should change those. And then there's a bunch of jokes about Elvis that I can't remember why they were in there. I look back on this and think, I don't know why I ever would have thought that was a clever thing to put in, but we'll leave them in. They're good examples. So when you call re.match, it will only ever consider a string to match if the regular expression matches starting at the beginning of the string. It doesn't have to match the entire string to work, but unlike grep, it's not going to go in and look for a case where the pattern matches. It starts matching the pattern at the beginning of the string, and if it can't do that, then the match is considered not to exist. And the reason for that is because there is a different function you could use if you just want to go look inside the string for matches. We will talk about that later. So if we want to just ask the question if a match exists, which for the early examples is all I want to do, then we could wrap up a call to re.match in a function like this. Basically just ask if the return value is none or not. And we know that because the value none in Python is considered to coerce to the value false as a Boolean value, we could just use this if statement, if re.match. And I'm going to do that because I mostly want to talk about the syntax and go through some examples in the first bit here. So if I want to ask whether a string begins with a non-negative integer value, so non-negative being a key word there because that way there's no negative sign at the beginning, what I want then is one or more digits from 0 to 9. And there are a couple of ways of doing this. Using what we've already seen, we can write it like this. Give me one digit from 0 to 9, and then as many more as you want. So I double up on the square brackets. I could also use the plus operator, and it turns out that there's a special qualifier \d that we'll see in a minute that we could use as well. So the functions that I care about mostly for this sequence are re.match, which is just ask whether, here's a string, here's a pattern, tell me whether the string begins in something that matches the pattern, and then return an object, if so, return none otherwise. re.findAll, where I give you a pattern and a string, and it goes in and finds all non-overlapping instances of that pattern in the string. And then finally re.sub, where I give you a pattern, I give you a replacement, and I give you a string. And the goal is to search the string, find every instance of the pattern, and replace each instance with the replacement. So this is basically search, and this is search and replace. In Python, the meta symbols, this is just a summary of the meta symbols. The meta symbols you might use are the same ones we saw earlier for grep, so things like the dot and the caret and the $sign. But there are also these nice convenient character classes you can use. When you write \w, then this is supposed to mean a word character. And for some reason in Python, they consider word characters to be letters, numbers, or underscores. So when you write a \w, that's telling it match one character that's either a letter, number, or underscore. \s is any whitespace character, and that's great because we don't want to worry about all the different kinds of whitespace that could exist, so tabs and spaces and weird Unicode things. \d is any digit between 0 and 9, so \d is a surrogate for writing square brackets 0 to 9. And then this is a weird one, \b. So let's take a look at a string here. So here's the string, hello world. And we know that in this string, this is a space. I'll write it sort of like that. That's a space. \b is matching this invisible boundary here. So there isn't a character between the space and the W, or between the O and the space. But we could consider that to be the boundary between a word and something else, the space between a word. \b is considered to be this invisible boundary. If you want to match the word boundary, you can use \b. It's a bit of an acquired taste. It's quite helpful once you get used to it, but I wouldn't be surprised if it's a bit confusing at first. And then if you want to match an actual \, you use two backslashes. As usual, we use an escape character because we use the \ for other things. As far as other meta symbols go, we've got the star, the clean star, which matches 0 or more occurrences of whatever comes before it on the left. We have the plus, which matches 1 or more. The question mark matches 0 or 1, so not an unlimited number, just 0 or 1. There are these, which I don't use very often, but they exist. You can put an actual number in curly brackets, and that will match that exact number of repetitions, or some number in a range, if you put a comma in there. There's also this operator. This is the vertical bar, same as you might use for bitwise OR in C, which is to match one but not both of these two possibilities. So it's a way of giving two options for a pattern to match. We've already seen the square bracket operator, and then there are various grouping things. So we can use parentheses in our regular expressions, and that allows us to quantify combinations of things. So for example, this pattern here will match strings like AB, or just A, or A, B, 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 things like that. But what if I want to match sequences like AB, A, AB, AB? So I want strings of AB, AB, AB that go off into the distance. In that case, what I could do is I could put AB inside brackets and put a star on that. What this is saying is, give me 0 or more occurrences of the substring AB. And so it would match things that look like that. So being able to do that, and then I'll define what's happening in this situation in a couple of videos. But being able to do that, of course, is really helpful. Okay, so what I want to do as far as breaking down the rest of this weird pre-recorded guest lecture is I'll go through some examples of how to design patterns given a particular pattern matching task. That'll be the next video. And then we'll talk about things like how to search for all occurrences and how to do search and replace. And then maybe I'll post as well an optional video about the mechanics of what's really going on behind the scenes.